Hi, my name is Quentin. I've been working at the CA for about 4 years, and today I'm going to present to you a progress report on RobinHood v4. Now, most of you in the audience, I expect, have at least heard about RobinHood, but do you really know what it is? RobinHood is a project that aims at providing efficient and easy-to-use means to replicate and query any file system's metadata. Put simply, the way it works is it takes all your file system's metadata and puts it into a database. That means that if you're looking for things inside your file system, you can query the database instead of the file system itself. Provided you place indexes on the right fields in your database, this can provide you with much better performance, much better search performance. Now, what is new with RobinHood in 2020? One thing that is new, and I think very important, are extended attributes, or exatters. You know them, they exist on file systems, and they can be loosely defined as custom metadata attributes. On file systems, there are key value pairs that you attach to inodes. The value is a binary blob. This is different on RobinHood, where the value can be structured data. This is important for RobinHood because it means that you can attach user-defined information to your files, and you can actually query it later on. This is because it is structured data. By structured data, I mean that we support string-indexed mappings, sequences, and scalars, such as sized integers, strings, and binary blobs, because those are also useful. This feature can be used to implement support for example, Luster's progressive file layouts. You could store, for example, a progressive file layout as a sequence of composite layouts, which you would then be able to query. That way, for example, if one of your OST crashes or has a problem, or I don't know what, and you want to list all the files that are now inaccessible to, for example, WARN users, you would be able to build a query in RobinHood that would match all the files that have at least one stripe on this particular OST. Now, when the feature of exatters is implemented and supported and available right away on RobinHood, the support of Luster's progressive file layout, for example, is not. I'm hoping that once RobinHood is released, the Luster community will step up and try to implement this. This might be just wishful thinking, but one can always hope. Another thing that is different with RobinHood exatters is that, on file system, you can link the same inode twice in your file system, in the namespace. That's called a hard link. So basically, you have two different paths that lead to the same actual file. On a file system, you can only attach exatters to inodes. And this can be problematic if you want to attach different information to different paths. For example, if you only ever want to apply a certain policy, because RobinHood at the beginning was a policy engine, if you only want to apply a certain policy for entries that are in certain directories, you want to be able to distinguish those that are in, for example, directories named backup from those that aren't in directories named backup. Probably or presumably because you don't want to delete files that are under a backup directory. With RobinHood, this is possible because you can actually attach exatters to namespace entries. You can even do fancier things like attaching exatters to namespace entries and also the inodes themselves, and you are able to recover all of them at the same time. In RobinHood, this is primarily used to attach a path exatter to namespace entry that allows you to know exactly the full path of an entry just from looking at its record in the database. Another thing that changed in 2020 and is also very important are FS events. FS events I sort of spoke about last year, and if I had to define them, I'd say they are metadata update records. They are in some ways very similar to Lustre changelog records, and that is actually not innocent. They come in 5 flavors compared to Lustre's changelog records, for which there are probably more than 15 different types. With RobinHood, we are interested in much less diversity of updates. We only care about those 5: upserts, links, unlinks, deletes, and excites. 3 of those are inodes related metadata updates. Those are upserts, deletes, and excites that attach to inodes. 3 of the ones that are left are namespace related. This is link, unlink, and etc. Etc is mentioned twice because, as I just said, they can both be attached to inodes or namespace entries. So there are actually 6 different types of FS events. One very important property of FS events is that they are replayable. What this means in practice is that if you have a program that, say, processes FS events 4 at a time in order to apply them on a RobinHood backend, and for some reason your program crashes while processing a batch of 4 FS events. The program crashes. Now it is back up, but do you know exactly which FS events were applied on the database and which were not? Well, you don't have to care with FS events because they are replayable. So if you apply them twice on the database, this is not an issue. It's slightly more complicated than applying twice any FS event. You have to apply FS events in order, and you can't just pick one and apply it. But in this instance, if you crash during the processing of a batch of 4 FS events, you can simply start again from this very batch and apply them all together, and it will still work. This is a very important property. This makes crash recovery that much simpler. One thing that we also did with FS events this year is we implemented the support for YAML serialization and deserialization. This is an important step towards distributed processing of FS events, such as depicted in this graph. So what you see here is the idea of how distributed FS event processing should work. So at the beginning you have a Lustre MDT, which emits Lustre changelog records, which are collected by the green node, which then converts this into sparse FS events and serialize them in YAML. Sparse because not all the information that is contained inside changelog records, changelog records, Lustre changelog records, do not contain all the information you need to update a RobinHood backend. You have to query the file system a little to get all the information you need. So the first step is to produce a sparse FS event from which there are parts that are missing. You serialize this as YAML and you send it on the network to the worker pool in orange, which are the nodes that are tasked with querying the file system and upgrading, if you will, FS events to full FS events. Those are then serialized as YAML and sent to a worker pool of blue nodes, which will apply them on your RobinHood backend. If you want to know more about how distributed processing for FS events is designed for RobinHood, check out last year's presentation. I think I did a pretty good job of explaining how I designed it. While working on this serialization feature, I developed a small wrapper around libyaml, which I called MiniYAML. It is available on GitHub on the CAHPC repository. if you want to work in C with YAML and you want to serialize and deserialize C structure especially, I think it's a nice project and you should probably check it out. Now, what's new? What's next? What's next in 2020? So those are features that I hope will be available by 2021. At least I very much hope so. The first one is full luster changelog support. So that means that now that I know how to serialize and deserialize FS events in YAML, I want to be able to produce FS events from luster changelog records. And as soon as this is available, you will be able to incrementally update your RobinHood backend with just a stream of luster changelog records. Another thing that is also extremely important for this feature to be useful in production is you need, and I need to implement an FS event deduplication mechanism. So luster changelog records, they describe each and every update on the file system, and sometimes those updates, they cancel each other out. Or sometimes if you get a user that writes 10 times on a file and opens and closes the file each time, you only really care about the last update, right? You only want to process the last event and query the file system for the last event, look at what the file looks like, update its metadata in RobinHood, and you don't want to do this 10 times. So considering how many events can be deduplicated in a luster changelog record stream, it is very important that we have this deduplication mechanism by 2021 to put RobinHood in production. RobinHood is probably going to be fast enough to sort of work before that, but I can't be sure, and I really want to have this working before actually advertising RobinHood for production. And the last thing that would be nice to have by 2021 that we probably won't because it's a lot of work is a pattern binding. The idea is that right now RobinHood is architectured as mostly a library plus a set of tools, and this library is implemented in C, and so if you want to interact with it, you have to write C programs. This is okay for developers, I think, but and also it provides a lot of performance. But if you're an administrator and you just want to do something with RobinHood, you probably don't want to use full-blown C programs for this, and you'd rather write a little Python script. And that's what I mean by Python binding. You would be able to write scripts such as this one. This one is a very basic example, which I call purge.py. What it does, it uses standard Python libraries like datetime to fetch all the entries that have an A time that is older than 90 days, and it queries the RobinHood backend for this, and it unlinks every entry that matches these criteria. This is what you would be able with the Python. You would be able to do with the Python binding, and I think it's pretty interesting if you think about it. It would allow us not to have to implement a fully fledged policy engine, and rather let users do their things basically. And now it's time for a demo. So I have this here. Nope. I don't want to do this. Alright, it's gonna stop. I was just playing it a moment ago. Let's go. So this demonstration I run on CentOS 8.2 with PowerTools enabled. 8.2 is going to be the first CentOS release that is going to be compatible with RobinHood v4. Prior releases use outdated versions of important packages for MongoDB, which I don't intend on supporting. So focus on CentOS 8.2 if you want to support if you want to use RobinHood v4. As you can see, I fetched the repositories from GitHub. I installed the build dependencies. There aren't that many of those. It's really just the bare necessities. Yes. At the time I ran the demonstration, there was a bit of latency on the network, so this is why it takes a little bit of time to fetch packages from EPEL. And yeah, once the build dependencies will be installed, I will build the different projects, and I will install them using Mason and Ninja. Those are build systems that aim at replacing things like AutoTools, and they are much faster, and it is a pleasure to use them to build a project. You see, I ran all the builds, I installed everything, and it took like 2 seconds. Now I add the MongoDB repository to be able to install MongoDB, because MongoDB changed its license like 1 or 2 years ago, and most distributions have decided that this new license is not compatible with their distributions, basically. And so I have to use MongoDB's own repository to install a rather up-to-date version of the database. I then launched the database with systemctl, and I create a template file system just to show you how you would go about using RobinHood. So I create a bunch of files and directories, and then I sync those with RobinHood. So to sync them, I use RBH sync. RBH sync is not really something that you use to scan a file system. It is just that it is able to synchronize 2 RobinHood backends, and file systems are actually one of the 2 supported RobinHood backends. So what you do is you actually tell RobinHood, here is a POSIX backend, which is basically just any file system. Its root entry is myfs, which is the root directory that I created, and I want you to synchronize this with a Mongo RobinHood backend, which doesn't exist yet, that I want you to name myfs. This is very fast, but this is not the point of the presentation. And after this, you can use RBH find to sort of report on what RBH sync just said. It queries the database directly, and it provides you with an experience comparable to that of GNU-Find. The command line is very similar. It's actually almost a option for option clone, although not all of those are implemented, but it is on the roadmap. Here I just want to show that actually the file system was correctly scanned, and all the entries are effectively in the database. The numbers match. The number is 16 times 16 to have all the files, 16 files per 16 directory. The other 16 is for the number of directories, and the 1 at the end is for the root of my template file system. After that, I show you how you can use RBH find, just like GNU-Find, to report only directories or only files. And you can do complex things like only files that have a name that end with 3, for example, and you can see only files that have a name with 3. That concludes the presentation and also the demonstration, and if you have questions, I'm happy to take them now. Thanks.